I'd like to talk a little bit about an equation called Schrodinger's equation. But before I want to talk about Schrodinger's equation, I want to talk about something called the wave function. And before I talk about the wave function, I'm going to talk about something called phase. Okay, first of all, I'm going to look at this demo that I've got in Desmos that is entitled 3 Waves in Phase. And you'll notice that the red one, let me turn off the other two. I'll bring this down to the bottom. Okay, the red one, that's just a sine wave. The green one looks a lot like what you call the normal distribution. And this one is called the sinc function. And the sinc function looks like, let's see, where is this sinc function? Right here. I've got it defined sinc x equals sine x over x. All right, but the part of the equation that I want to talk about is this part right here. And it goes 2 pi x over lambda minus 2 pi t over period. And notice all three of these functions, sine, phase, 3, okay. This one is a little different because I tried to offset it. Let me get rid of that part so that it's with the others. Now, I've basically got, and this, okay, I want this to be phase. Okay. Okay, now you can see that all three of those equations are in phase. And if I wanted to, I could represent them all together by plus this, oops, yeah, plus this, and you get kind of a funky looking wave, but they're all in phase. Let's make it a little brighter. Okay, so all those functions are in phase, and the thing that makes them in phase is just putting this phase as a parameter in the function, which was 2 pi x over lambda minus 2 pi t over the period. And that tells it to move to the right. If I changed it to a plus, move to the left. Okay. And one of the things that's going on is I'm animating it with respect to t. Time is moving forward, so the thing is moving to the left. Then if I subtract, time is moving forward and it's going to the right. So this is the phase. Now, what is a phase caused by? Well, imagine that we have a particle or an emitter, and the emitter is moving along to the, I should pause this. Pause. The particle is moving to the left, and it's emitting a sine wave. So here it emits a peak of a sine wave, and here it emits the second peak of the sine wave. We can tell based on when it releases the first sine wave. Oh, and by the way, this is intended to be a space versus time graph, so that the particle is moving to the left. So this is the before and this is the after, and we have the particle moving to the left, and it releases the peak of a wavelength, a peak of a photon here, and the peak of the next photon here. So since that is a peak and that is a peak, from our point of view, this here is the wavelength and this here is the period. Now, if I brought it back so that the particle was stationary, it would look like this. Here is the peak, here is the next peak, here is the wavelength, and here is the period. So then, if it was moving, instead of moving to the left, it was moving to the right, then the photon that's shooting to the right is what they call blue shifted. So the wavelength and the period are both smaller. Now there's a relationship between the phase velocity and the wavelength and the period, and it looks like this. The velocity of the phase is equal to the wavelength divided by the period. So for that photon, you'll notice the velocity of the phase, regardless of where we put the particle, how fast we make the particle move, the ratio of the wavelength divided by the period is always going to be the same. And that is always the speed of light. So that means we can solve this for lambda, make it lambda equals CT. Come over here and replace lambda with CT, so we got 2 pi over CT minus 2 pi over T, and we can describe this as the phase is 2 pi over T times the quantity, let's see, this was x and this was t, 2 pi t, 2 pi x over lambda, 2 pi t over t. So it is x over c minus t. There we go. So this is one description of that phase. We can also say, solve this for t, and we get t equals lambda over c, or 1 over t equals c over lambda. So that makes this expression be 2 pi over lambda minus 2 pi c over lambda t. And then, I forgot the x, and so this makes the phase 2 pi over lambda x minus ct. So these are two other expressions for the phase. And one of them is in terms of the period and the speed of light. The other one is in terms of the wavelength and the speed of light. So for a moment, I want to mention that I can actually plug the phase, or I can actually plug one of those functions like sine of the phase into this equation here, and sine of the phase into this equation here. And what happens, I'm going to actually get rid of the v of x comma t part, get rid of that, and just kind of calculate both sides. I made a table down here. So what I'm going to do is use this sine 2 pi x over lambda minus 2 pi t over t. This is kind of the standard state phase description. Then I put it into a description with lambda and c. And then I put another description with period and c. What happens when I use the deBroglie expression? This is the left-hand side, where they take h bar del del t of psi. When I'm plug in the general form with the lambda and the t, then you end up with E psi equals HF psi. Then on the right-hand side, where we take 1 over 2m times h bar squared del del x squared, you end up with 1 over 2m h over lambda squared. You may be wondering, why in the world is this m here? Why is there an m on the left-hand side? Why is there no m on the left-hand side, but there is an m on the right-hand side? Well, it turns out it's in the h. The quantity h is in kilogram meters squared per second. So if I square it, if I square h, then I got kilograms squared meters to the fourth per second squared. Anyway, the kilograms is canceled out by kilograms squared is canceled out by the mass to give you kilograms, and over here kilograms is not canceled by mass, so you end up with kilograms. Anyway, it comes out in joules either way. Joules on the left, joules on the right. Now, if we use the expression that's in terms of the speed of light and wavelength, taking the derivative with respect to t gives us e psi equals hc over lambda psi. But the second derivative on the right-hand side, we'd pop out 2 pi over lambda twice, and we end up with 1 over 2m h over lambda squared psi. On the other hand, we do the same thing with the version that is in terms of the speed of light and period, and we get E psi equals hf psi over here, and p squared over 2m equals 1 over 2m h over ct squared. So here, momentum is h over lambda, momentum is h over c times the period, or hf over c. Over here we get E equals hf and E equals hc over lambda. Now all that is pretty well established. What you get out of deBroglie, or get out of Schrodinger's equations applied to light waves. But what has always seemed a little bit less clear is what happens when you try to apply the deBroglie or Schrodinger equations to an equation for a particle, or a particle with mass. For a moment, to describe the deBroglie wave, I want to consider the idea that a particle might be described as a vibrating sphere, just a sphere that is like going out and in and out and in. But I want you to notice something. The velocity of the sphere appears to be 0, but if you look at the way the purple line hits the edge, you could kind of think of it as that wave hitting all parts of that outer surface all at once. And so if you took the delta x between this event and this event, you would have a finite x. And if you took the delta t between the same two events, you would have essentially 0. So you could say that the velocity of that wave over that space is infinite. It's delta x finite delta x divided by a 0 delta t. But I'm going to look at it from a different point of view, where the speed of that wavefront coming out to the edges is still the speed of light, but it actually hits from back to front. So now we've got a positive velocity for this, because the amount of distance between here and here is still a finite amount, and the amount of time between there and there is very small, but it is not 0. Now you remember earlier I had the idea of a peak here and a peak here with the photon moving to the right, but now I'm going to get rid of that wave and think in terms of that circle. This time we've got a peak here and a peak here, but the peak occurs at all locations at the same time. This is like if you, instead of thinking in terms of the circle, we think in terms of think of it in terms of a wave hitting a shoreline. And if the wave hits the shoreline so that it's not at an angle, then the wave will, then the speed of the wave across the shoreline is infinite. But if it hits at an angle, then we'll have the wave strike over on this side first, and then later on this side. Now this has a period coming this way and a wavelength going this way. There's no limit to this wavelength. The wavelength can go all the way to infinity when we have it stopped. And but the period maxes out here at 0, and this period gets smaller and smaller and smaller as we approach the speed of light. Now, as we do this, or as we change the velocities, the black line has a slope of v equals beta c, while the green line has a slope of v equals c over beta. They're not exactly reciprocals of each other, but they would be if we said v over c would be c, and v over c would be 1 over beta. Actually, since the graph is described with c equals 1, the two slopes are reciprocal of each other in this diagram. Now, what happens when we put in that phase velocity? Basically, here, instead of our velocity being c, which it was for light, we are replacing that velocity, our phase velocity, with c over beta. That was the slope of the green line. And what happens when we plug in sine of this term here into the Schrodinger equation, the value of E psi here gives us, well, first of all, I'm going to go ahead and use the relativistic expression for E. So I'm going to say mc squared cosh phi, and go ahead and give the value of beta is hyperbolic tanh of phi, and you end up with lambda is equal to h over mc sinh phi, which is the relativistic momentum. You do the same thing over here with the p squared over 2m and take the second derivative, and what happens is we end up with the momentum being h over lambda, or lambda is h over p, which is the same thing. Plug the version in terms of period into the equation, and we end up with mc squared cosh phi is equal to hf, which means that the deBroglie frequency is very, very high, much higher than you've probably heard in most texts. So here is what we don't really get the left-hand side of Schrodinger's equation equaling the relativistic kinetic energy. We get relativistic total energy on the left-hand side instead of relativistic kinetic energy. We also don't exactly get the right-hand side of Schrodinger's equation giving us the relativistic kinetic energy. But we get something very close, because mc sinh phi squared is very close to, or sinh squared phi is very close to cosh phi minus 1. Actually, let me go ahead and graph those. Okay, so here are the two expressions put next to each other. Actually, it was sinh squared phi over 2 versus cosh x minus 1. And you can see they are pretty close together if you don't go above like 0.2 or so. Maybe there starts to be a little bit of variation if you look in here really close. Now, I also considered what it would be like if we plugged in, instead of using that phase, we just tried using the regular velocity of the particle. So x minus the regular velocity of the particle, beta c times t. And what happened then was when I plugged things into Schrodinger's equation, I ended up with the left-hand side giving me something like 2mv equals h over lambda, and the right-hand side, I'm sorry, setting the left-hand side equal to the right-hand side in the frequency description gave me 2mv squared equals hf, and setting the left-hand side equal to the right-hand side in the wavelength description gave me the 2mv equals h over lambda. I don't know, or I'm not sure if there's anything meaningful to find in those results. I just was curious to see what they would work out to be. And anyway, this is 4 times the kinetic energy of a particle here, 4 times 1/2 mv squared. And this is 2 times the momentum of a particle, which would generally be mv, the Newtonian version of it anyway. Okay, well, hopefully that kind of gives an idea of what I'm trying to do here in section 7, the wave function.